Hi everyone. Here is the 12th question of Schrödinger's test. Test the AI's thinking ability. The question is the atoms of the same isotope, are they identical? Or atoms of the same isotope identical? ChatGPT's answer: yes. In conventional physics and chemistry, atoms of the same isotope are considered identical, and isotope is defined by a fixed number of protons, neutrons, and electrons. And the atoms share the nuclear composition, are treated as indistinguishable in all intrinsic physics properties such as mass, charge, and decay behavior. In quantum mechanics, this indistinguishability is taken as fundamental principle. Atoms of the same isotope are regarded as identical particles, meaning that no physical measurements can distinguish one from another. Any difference observed in behavior, such as timing of radioactive decay, are attributed to the inherent randomness of quantum process rather than to differences between individual atoms. Accordingly, radioactive decay is described statistically, while individual decay events occur at unpredictable times. All atoms of the same isotope are assumed to share the same decay probability per unit time. Differences in decay time do not imply difference between atoms, but reflect the probability nature of decay process. This is ChatGPT's answer, but of course this is a human answer. ChatGPT only repeating it. Okay, here's my answer. Atoms of the same isotope are identical only in having the same number of electrons, protons, and neutrons. Similar to human beings, one head, two eyes, one nose, and one mouth, and 2 ears, and 2 arms, 10 fingers, and so on. Radioactive decay demonstrates the non-identity in behavior. If atoms of the same isotope are physically identical as concrete objects, there would be no factual basis for their decay to occur at different times. In general, it is logically safer to assume the atoms sharing the same number of electrons, protons, and neutrons are not identical as physical individuals than to assume the opposite. Atomic nuclei is a combination of protons and neutrons, and there are many possible ways these constituents can be arranged or combined within the nucleus due to the internal forces. Kind of like a magnet, or kind of like a piece of iron, or a piece of cast iron. Internally, it can be magnetized. Different arrangement of iron atoms can exhibit magnetism or not. So identity, therefore, holds at the level of the observation and the classification, not at the comprehensive level of physical behavior and properties. For example, atoms of the same elements do not always have identical in chemical reactions, nor do hydrogen atoms participate identically in nuclear fusion. Likewise, a probability model that treats, say, 100 balls of 50 black and 50 white as identical objects put in the bag, if you calculate the probability of picking one of them out, and it is obviously always half and half. However, neutrons and protons are not just black and white balls. They are more like magnets painted a different color. Say, suppose if this 100 balls are 100 magnets painted 50 black and 50 white, and you put in the bag, and then you calculate the same calculate the problem for the same question, picking out a white magnet or a black, then the result is no longer half and half. It will largely depend on, or completely depend on, how these magnets are put into the bag initially. Because once they gather together, that formation is rather stable because of the forces between neutrons and protons. And this is where I say, where the God played dice with the universe. When these balls put together, there are different ways of there are many different formations, just like a bunch of magnets put together. They may form even stronger magnets. They may, due to the internal cancellation, maybe a weaker magnets. And that difference is the difference between atoms of the same elements or the same isotope. And of course, current human endeavor, either in physics or chemistry, we do not observe these differences yet. Or when we do observe these differences, we kind of deny it and call it statistical. Statistics need, I don't know how many samples you have to test to draw a definite statistic conclusion, and whether even entire human history of physics and chemistry is enough, because they are only like a few hundred years. Few hundred years really is nothing to universe, although it's very long to us. And so still logically, atoms of the same isotope, radioactive or not, are not identical. Assuming them identical is not as safe as assuming them not identical, especially there are only finite of them. You have to compare them all to say they are identical. If you left one out, not compared, that one could be different logically. Okay, that's all.